Now let's talk about the birth of a croissant. It all begins not with a bang, but with a mix. The main players here are simple, yet they are the foundation of everything that follows. We're talking about flour, water, yeast, sugar, and a little bit of salt. The flour provides the structure, its proteins forming gluten strands that give the dough its stretch. Water is the activator, waking up the yeast and hydrating the flour. The yeast, a living microorganism, is our leavening agent. It will consume the sugar and release carbon dioxide gas, which is the secret to a light, airy texture. And salt? It's not just for flavor. It controls the yeast's activity and strengthens the gluten network. These ingredients are combined in massive industrial mixers, giant stainless steel bowls with powerful rotating hooks that knead the dough to perfection, ensuring everything is uniformly combined and developed. The initial dough, what the pros call the détrempe, is just the beginning of our culinary construction project. Think of it as the concrete foundation of a building. It needs to be strong but also pliable. Once the mixer has done its job, the dough is smooth and elastic. It's then given a short rest, a little nap, if you will. This resting period, known as fermentation or the first proof, allows the yeast to get to work and the gluten to relax. This makes the dough easier to handle in the next, very crucial stage. Without this rest, the dough would be a stubborn, uncooperative mess, fighting back against the machinery that is about to shape its destiny. It's a delicate balance of science and timing, all happening on a massive scale. Next up is the fat. In the world of croissants, fat is not the enemy, it is the hero. While a traditional French patisserie might use high-quality butter, a large-scale factory often employs a specialized margarine. This isn't your average toast spreader. This is a carefully engineered fat designed to have a specific melting point and consistency. It needs to be firm enough to be rolled into a thin sheet, but pliable enough not to tear the delicate dough. The fat is what will create the hundreds of flaky layers we all love. It's a barrier, a separator. When heat hits it in the oven, it will melt and create steam, pushing the layers of dough apart and creating that signature honeycomb interior. The quality and handling of this fat are non-negotiable for a good result. So we have our rested dough ball and our block of specially formulated fat. These two components are about to become one in a process known as encasing. The dough is rolled out into a large square. The block of fat, which has been shaped to be slightly smaller, is placed in the center. Then the corners of the dough are folded over the fat like you're wrapping a very important, very delicious present. It's sealed up tight, ensuring no fat can escape. At this point, we have a packet, a parcel of dough and fat. This is the fundamental building block from which every single croissant will be born. The stage is now set for the magic of lamination to begin. Welcome to the lamination station. This is where our dough and fat packet undergoes a transformation. The goal is simple: create as many thin, alternating layers of dough and fat as possible. To do this, factories use a machine called a sheeter. Think of it as a giant, automated rolling pin. The dough packet is fed through a series of rollers that gently press and elongate it into a long, uniform rectangle. The process must be precise. If you roll it too thin, the layers will merge. If you don't roll it enough, you'll end up with a bready, dense product. The machine controls the thickness down to the millimeter, ensuring consistency batch after batch, which is something a human baker would struggle to achieve on this scale. Once the dough is stretched out, it's time for the turn. This is a fancy term for folding. A common method is the letter fold or single turn. Imagine a long sheet of paper. You fold 1/3 of it over the middle, and then you fold the remaining third over the top of that. Voila, you have 3 layers. Our dough sheet undergoes this exact process. This folded packet is then given another 90-degree turn and sent through the sheeter again. The process elongates the dough once more, and then it's folded again. Each fold multiplies the number of layers. Starting with 3, the next fold gives you 9, then 27, and so on. It's exponential layering. Now all this rolling and folding generates friction, which creates heat. And heat is the enemy of lamination. If the fat melts and gets absorbed by the dough before it hits the oven, you lose your layers. Goodbye, flakiness. To combat this, the dough must be chilled between turns. After 1 or 2 folds, the large sheets of dough are sent to a cooling chamber. This allows the fat to firm up again and the gluten in the dough to relax. This resting period is critical. Rushing this step is a recipe for disaster, resulting in a greasy, tough croissant. The cycle of sheeting, folding, and chilling is repeated several times until the desired number of layers, often numbering in the hundreds, is achieved. After the final fold and chill, we are left with a massive, multi-layered slab of dough. It's a thing of beauty, a testament to mechanical precision and food science. If you were to cut a cross-section, you would see incredibly thin, alternating strata of dough and fat, almost too fine for the naked eye to distinguish. This final laminated dough is the culmination of all the previous steps. It's now ready to be shaped, but its potential for a light, flaky, and shatteringly crisp texture has already been locked in by this repetitive, carefully controlled dance of folding and chilling. The foundation for a perfect croissant has been well and truly laid. Our journey continues as the large, perfectly laminated slab of dough moves to the cutting and shaping line. This is where geometry takes center stage. The dough is carefully fed into a machine that first cuts it into long, wide strips. Then, a specialized cutting roller, a marvel of engineering, descends upon these strips. This roller is covered in blades arranged in a pattern that stamps out perfect, elongated triangles of dough, one after another, with incredible speed and precision. The leftover dough scraps are collected, though they often can't be reused for croissants as the layering has been compromised, so they are typically repurposed for other baked goods. It's a model of efficiency, minimizing waste while maximizing output. Now we have thousands of identical dough triangles, all lined up and ready for their final form. Each triangle moves along a conveyor belt to a shaping device. Here, a clever mechanism grabs the base of the triangle, the shortest side, and begins to roll it up towards its point. The machine mimics the gentle, even pressure of a baker's hands, ensuring the croissant is rolled up tightly enough to hold its shape, but not so tight that it can't expand during proofing and baking. As it rolls, the iconic crescent shape begins to emerge. Some machines even give the ends a slight curve, perfecting that classic look we all recognize. Once rolled, the unbaked croissants, now called pâtons, look small and dense. They are a pale, doughy color and bear little resemblance to the final product. But inside, the potential is waiting. All those layers of dough and fat are coiled up, ready to spring into action. The little crescents are then carefully transferred by automated arms or conveyor systems onto large baking trays. They are arranged in neat rows with plenty of space between them. This spacing is crucial. They need room to grow, to expand to their full glory in the next stages. It's an assembly line of pastry, a continuous flow of creation from a flat sheet of dough to a tray of perfectly shaped croissants. This entire shaping process happens at a breathtaking pace. What would take a skilled baker hours to accomplish by hand, these machines can do in minutes, producing thousands of perfectly uniform croissants. This level of consistency is a hallmark of industrial food production. Every croissant has the same number of layers, the same weight, and the same shape. This ensures that when they move to the next stages, proofing and baking, they will all behave in the exact same way, leading to a predictable and reliable final product. The army of tiny dough crescents is now ready for its next mission, to rise. The trays of newly shaped croissants are wheeled into a proofing chamber. Think of this as a warm, humid spa day for dough. The environment inside is carefully controlled, typically around 27 degrees Celsius, with high humidity. This is the ideal climate for our friend, the yeast. Warmed and cozy, the yeast goes into overdrive, feasting on the sugars in the dough and releasing a large amount of carbon dioxide gas. This gas gets trapped between the hundreds of dough layers, causing the croissants to puff up and expand significantly, often doubling in size. The humidity is key here, as it prevents a dry crust from forming on the outside, which would restrict this expansion. This is the final rise, the moment the croissant develops its light, airy structure. Once perfectly proofed, the swollen croissants are ready for the oven. They are transported into massive tunnel-like industrial ovens. As they travel through this cavern of intense heat, several things happen at once. The oven spring occurs as the heat gives the yeast one final burst of activity. Then, the fat that was so carefully layered melts away. As it melts, it releases steam, which powerfully forces the dough layers apart, creating that signature flaky honeycomb interior. The sugars and proteins on the surface undergo the Maillard reaction, a beautiful chemical process that gives the croissants their deep golden brown color and delicious toasted flavor. The result is a perfectly baked, hollow, and gloriously flaky pastry. After baking, the croissants are cooled on racks. Then comes the moment we've all been waiting for, the filling. How does that creamy cocoa goodness get inside a sealed pastry? The answer is injection. The cooled croissants are placed on another conveyor belt that moves them past a filling station. Here, automated nozzles like tiny injectors pierce the underside or end of each croissant. With a precisely measured puff of pressure, a dose of rich, smooth cocoa cream is injected into the hollow center. The machine is calibrated to deliver the exact same amount of filling every single time, ensuring that the last bite is just as satisfying as the first. The tiny hole left by the nozzle is barely visible. Finally, our filled croissant is ready for its journey to you. The last step is packaging. Individual croissants are fed into a flow wrapping machine. This machine envelops each one in a sheet of plastic film, which is then heat-sealed to create an airtight package. Sometimes a process called modified atmosphere packaging is used, where the air inside the package is replaced with a gas mixture, like nitrogen, to prevent spoilage and keep the croissant fresh for weeks. The packaged croissants are then stamped with date codes, bundled into boxes, and shipped out. From a simple mix of flour and water to a filled, flaky, and fresh pastry in your hand, it's a remarkable journey of science, engineering, and a little bit of baking magic.